Hey everybody, these are the notes for homework number 12, graphing rational functions and even and odd functions. So let's just get started here. A rational function is a function that is a polynomial divided by another polynomial. Some examples: f of x equal to x squared plus 3x plus 2 over x squared minus 2x plus 1, both polynomials. G of x equal to x plus 3 over x cubed minus 4x squared, both polynomials. And h of x equal to 4 over x squared plus 9. Even 4 is a polynomial. Again, not very exciting, but it is. I'll point out that in this first rational function, the degree in the numerator is 2. The degree in the denominator is also 2. For the second polynomial, the degree in the numerator is 1. That's the highest power of x. The degree in the denominator is 3, highest power of x. For h of x, the degree of the numerator is 0, right? The highest power of x is x to the 0th, which you didn't write, and the degree of the denominator is 2. That becomes a little bit important when we talk about horizontal asymptotes in a minute here. When graphing rational functions, we look for 4 different things. Specifically, if f of x equals p of x divided by q of x, we find the y-intercept by setting, you can set the whole function equal to, sorry, by setting x equal to 0, apologies, as we usually do, right? For any function, we find the y-intercept by setting x equal to 0. We're going to find the x-intercepts by setting the whole thing equal to 0. So we're going to set f of x equal to 0. But what I'm going to point out is what's going to end up happening is we're going to multiply both sides by q of x. So that really becomes setting p of x over q of x equal to 0. But then if you multiply both sides by q of x, that's really just the same as setting q of x equal to 0. So while you can do this, it's easier just to set the numerator equal to 0 if you're trying to find the x-intercepts. We're going to find vertical asymptotes by setting the denominator equal to 0. And then we're going to find horizontal asymptotes by comparing the degree of the numerator with the degree of the denominator. So actually, I'm going to go back up to these 3 examples here and just talk about how this first example, since the degree on top and the degree on the bottom are the same, the horizontal asymptote is going to be y equal to the leading coefficient here dividing by the leading coefficient here. So it's going to be 1 over 1, which is 1. Here, since the degree on top is 1, which is less than the degree on the bottom, the horizontal asymptote is going to be y equal to 0. Same deal here. The horizontal asymptote would be y equal to 0. So if the degree of the top polynomial is the same as the degree of the bottom polynomial, then we look at the quotient or fraction of the leading coefficients. So just giving you one more example here, if your function was, say, f of x equal to 2x cubed plus 1 over 5x cubed plus 4x squared, then the horizontal asymptote would be y equal to 2/5, because the degree on top and the degree on the bottom are both 3, and so the horizontal asymptote is the quotient or fraction of those leading coefficients, 2 over 5. And then we'll talk about more how that kind of looks when we graph these next few ones. A few more things to say, though, and then we'll get there, I promise. So in addition, or I should say additionally, just like when we were graphing polynomials, we're going to determine whether an x-intercept bounces off or passes through the x-axis by looking at the degree or multiplicity of the factor it came from. So for example, for f of x equal to x minus 3 squared times x plus 4 to the 5th, at x equal to 3, which would be one of our x-intercepts, well, since 3 came from x minus 3 squared, the graph is going to bounce off the x-axis, because when the degree or multiplicity is even, we get bouncing. Whereas at x equal to negative 4, which comes from this x plus 4 to the 5th power, at x equal to negative 4, the graph would go through the x-axis because that 0 comes from a factor that's raised to an odd power. Even more so, we're going to see another thing that has a similar sort of behavior. So in a similar way, we determine whether the graph goes in the same direction or the opposite directions on either side of a vertical asymptote by looking at the degree of the factor it came from. So for this example down here, to find the vertical asymptote of g of x, you would set the denominator equal to 0. And if we do that, if we set x minus 1 to the 4th times x minus 6 cubed equal to 0, you're exactly going to get x equal to 1 and x equal to 6. X equal to 1 came from a factor with an even power, So we're going to see that on either side of that vertical asymptote, both sides are going to go either both go up or both go down. So we say they have the same behavior on either side. It's kind of like bouncing off. You're staying either always above or always below the x-axis. Similarly, for x equal to 6, which came from this x minus 6 to the third power, since the power there, or the degree, or the multiplicity, all same words, or words are the same thing, since that power is odd, we're going to have opposite behavior on either side of the vertical asymptote. So one side's going to go up, one side's going to go down. It's kind of like going through the x-intercept from above to below the x-axis. In fact, it's very related, right? That's why you see the same kind of thing, right? When the power is odd, like here, odd power, you're going to bounce off. Odd power, you're going to have opposite sides. Even power, you're going to, sorry, I said bounce off with the odd power. Odd power, you're going to go through, sorry about that. Odd power, you're going to stay on the, or you're going to go on opposite sides. Even power, you're going to bounce. Even power, you're going to stay on the same side. So hopefully you can kind of see the connection there. All right, now examples. What are the asymptotes of f of x equal to 4x squared plus 9 over 3x squared minus 6x? So the way you're going to find the vertical asymptotes is by setting the denominator equal to 0. It's usually good to factor it. So I set 3x squared minus 6x equal to 0. I'm going to factor out a 3x times x minus 6, and that's going to equal 0. So I'm going to get either x equal to 0 or x equal to 6. I will also point out that for both of these asymptotes, they're both coming from factors that are raised to the first power. So both of these are going to have opposite behavior. I don't love just writing O. I'm going to write opposite, even though in the homework it says O. So they're both going to go like this or like this. So I don't know exactly what this graph looks like, but and I'm not graphing the whole thing. I'm just pointing out that like at x equal to 0 and x equal to 6, it's going to be something like, sure, it's going to be something like maybe this and this on. So on at x equal to 6, it's going up one side, down the other side. Same deal over at 0. It's going to go probably, I don't actually know what it looks like. It's probably go something like this and then like this, right? Down on one side is 0, up on the other side is 0. And then for the horizontal asymptote, we compare the degrees. Since the degrees are the same, it's a power 2 polynomial in the numerator, a power 2 polynomial in the bottom, or I should say a degree 2 and a degree 2. The horizontal asymptote is going to be y equal to 4/3. That's it. That's all there really is to say about the horizontal asymptote. And so we would plot that like this kind of. And then as you go further to the right, further to the left, the function gets closer and closer to that horizontal asymptote. Same idea here. For the asymptote of this, well, you'd start by to find the vertical asymptote, you'd set the denominator equal to 0. So x squared minus 2x plus 1 equals 0. You factor that, and it factors as x minus 1 times x minus 1, which we should definitely write as x minus 1 squared. So the only vertical asymptote is going to be x equal to 1, and the behavior is going to be that it's going to be on the same side, because that 1 came from a factor raised to an even power. So whatever this was looking like, you would have that it was going either both sides up or maybe both sides down. It's not doing by the same side. And here, the horizontal asymptote, since the degree on top is 1, and that's less than the degree on the bottom, which is 2, if the degree on top is less, then we know that the horizontal asymptote is y equal to 0, or the x-axis. We won't talk yet about what happens if the degree on top is larger than the degree on the bottom. We actually might not cover that at all, but that's kind of how we deal with horizontal asymptotes or rational functions. All right, the rest of these are just examples. So we're going to graph this function, f of x equal to 2 over x plus 1 squared. So we're going to look for all 4 things: y-intercept, x-intercepts, horizontal asymptotes, vertical asymptotes. And then we're also going to consider for the x-intercepts whether we bounce or go through, for the vertical asymptotes whether we're on the same side or the opposite side. So y-intercept, set x equal to 0. F of 0 is going to equal 2 over 0 plus 1 squared, which is just 2. So y-intercept is the point 0, 2. X-intercepts. So here's where we're going to do the thing where we set the whole thing equal to 0. So set the whole function 2 over x plus 1 squared equal to 0. But then if you multiply both sides by the denominator, you're just going to get 2 equal to 0 times x plus 1 squared. In this case, it's kind of dissatisfying because you're going to get 2 equal to 0, which isn't true. So we get no solution, which means there's no x-intercept. And I'd say a general statement that is true is that if your numerator can't ever equal 0, you're not going to get any x-intercepts. So no x-intercepts. Let's look at the vertical asymptotes. So with the vertical asymptotes, we're going to set the denominator equal to 0. So set x plus 1 squared equal to 0. And I think we can see right off the bat that we're going to get x equal to -1 as a vertical asymptote. And it's going to have same behavior, meaning both sides are going to go up or both sides are going to go down. So it's the same. And then finally, horizontal asymptote. The degree in the numerator, sorry, you can't see what, sorry, I'm kind of, sorry, cameras. I guess I can write it over here. Horizontal asymptote. The degree on the top is 0 because you don't have an x on top. If there's no x's on top or on the bottom, the degree is 0. And that's certainly less than the degree on the bottom, which is 2. So the degree on the top is 0. The degree on the bottom is 2 because if you multiply that out, you'd have x squared plus 2x plus 1. And so since the degree on top is less, your horizontal asymptote is going to be y equal to 0. And all that means is that as we move further to the right or further to the left in the graph is going to get closer and closer and closer to the x-axis. Let's graph it. So then after you found all the things you can find, you're going to plot them all on your usual xy coordinate system. So let's see. So I've got my y-intercept of 0, 2, no x-intercept, a vertical asymptote of x equal to -1. And then a horizontal asymptote of y equal to 0, which I'm not really going to draw, I just know it's there. So I know that from this point here, as I move further to the right, I have to get closer and closer to y equal to 0. I don't have any x-intercepts, so I can never cross the x-axis. And as I move to the left here, I have to go this way. There's no other choice, right? I can't go down and cross the x-axis where I don't have an x-intercept. And then, since my vertical asymptote was a same behavior vertical asymptote, I know that if one side's going up, the other side is also going up. And then as I move to the left here, I have to also get closer and closer to this horizontal asymptote of y equal to 0. And that's kind of it. We've plotted all the pertinent information. You might label this vertical asymptote as x equal to -1. You might label this point as 0, 2. But as long as you've written them somewhere, we should be good to go. Yeah, there we go. Let's do another one. I'm going to zoom out just a little bit so I can get hopefully a little bit easier to see everything I'm writing here. Okay, we're going to graph f of x equal to 2x minus 6 over x plus 2. Same usual steps. We're going to start with the y-intercept. Did I number them last time? If I did, that's kind of annoying. I did not. Good. I shouldn't start numbering things just because I want to. So y-intercept, x equals 0. F of 0 is going to be 0 minus 6 over 0 plus 2, which is -3. Great. So my y-intercept is 0, -3. X-intercepts. So again, you can set the whole thing equal to 0. But then if you multiply both sides by the denominator, we're going to get 2x minus 6 over x plus 2 times x plus 2 equal to 0 times x plus 2. X plus 2's cancel on the left side. That's why we're doing this, to get rid of the denominator. And 0 times anything is 0. So what we're left with is 2x minus 6 equal to 0. So what you can do is just start by setting the numerator equal to 0 when you're trying to find the x-intercepts. You could divide both sides by 2. You could just solve for x here. I kind of like factoring out a 2 because if I do it this way, it allows me to better see that, oh, my x-intercept is going to be x equal to 3. So I'm going to get 3, 0 as my x-intercept. And since it's raised to an odd power, that's why I like factoring out here so I can still see that the power is odd. I know that I'm going to go through the x-axis or cross through if you like. Okay. Y-intercept, x-intercept, vertical asymptote, or I should say vertical asymptotes. So generally, just kind of aside here, the y things, the y-intercept and the horizontal asymptote, you can only have one of. Whereas the x things, the x-intercepts, or the vertical asymptotes, you can have more than one of. So for vertical asymptote, we're going to set the denominator equal to 0, and we're going to get x equal to -2. And again, since even though there isn't a power here, I could think of this as x plus 2 to the first. That's going to have an opposite behavior vertical asymptote. So this is going to be an opposite behavior. Finally, horizontal asymptote. So I see that the degree in the numerator is 1. Degree in the denominator is also 1. So my horizontal asymptote is going to be y equal to 2 divided by the 1 that I didn't write there. Or y equal to 2. Cool. So there's all the pieces of information. Now we're going to graph it. So I've got a y-intercept at 0, -3. I've got an x-intercept at +3, 0. I know it's going to go through, so it's probably going to go like that. Maybe not, though. We'll see. Oh, sorry, you guys can't see that. Apologies. So it's probably going to go like that. And then my vertical asymptote at x equal to -2. And finally, my horizontal asymptote at y equal to +2. I don't like to make a sign chart here, but you certainly can if you want to. I'll point out that if you made a sign chart and you're really only going to put the x things on your sign chart, so the x-intercept of -3, sorry, +3, and your vertical asymptote of x equal to -2. Those are the places where the sign can change. Oh, darn it. Sorry, the camera just cut out for a second there. Apologies. Oh, camera, why are you such an issue? There we go. Sorry, I must have bumped the cord or something. So, sorry. Anyway, so what I was saying is we could make a sign chart here if we wanted to. And then if we pick a number, so if we look at our original function, I'm going to factor out the 2 on top, 2 times x minus 3 over x plus 2. If you pick a number larger than 3, I should say that's equal to f of x. Pick a number larger than 3, like 4, the top is positive, the bottom is positive, the whole thing's positive. Pick a number between -2 and 3, like 0, which we've already plugged in. You know, if we plug in 0, the whole thing's negative. Finally, if you pick something less than -2, like -3, the top's negative, the bottom's negative, so the whole thing is positive. So my graph is going to be above, below, above. So I don't really need that though, because I know that I have this point here, and from here to here, I'm going to hit that x-intercept, and then I'm going to go through because it's a through intercept. And then I'm going to get closer and closer to my horizontal asymptote. To the left here, I don't really have a choice. I kind of have to go down because I can't go up and cross the x-axis where I don't have an x-intercept. So I'm going to go down this way. And then since my vertical asymptote is an opposite behavior one, I know that if the one side's going down, the other side has to be going up. And then I only have the choice of getting closer and closer to my horizontal asymptote as I go out that way. And look, it agrees with my sign chart. From -infinity to -2, I am above the x-axis. I'm positive. From -2 to 3, I'm below the x-axis. I'm negative. And then from 3 to infinity, I'm above the x-axis. I'm positive. So not necessary to make a sign chart, but if you like to do it, that's great. More examples. Let's graph f of x equals x squared plus 4 over x squared minus 1. Okay, it's the same 4 steps every time. Y-intercept. Set x equal to 0. F of 0 is going to be 0 squared plus 4 over 0 minus 1. Sorry, 0 squared minus 1, which is 4 over -1, which is -4. X-intercept, or x-intercepts. Set x squared plus 4 equal to 0. I'm just setting the numerator equal to 0. And in this case, I get no solutions, right? If I have x squared equal to -4, I know I can't take the square root of a negative number, so no solutions, no x-intercepts. Excuse me. Vertical asymptotes, you're going to set the denominator equal to 0. And I do recommend factoring as much as possible here so that you can see the degrees of each factor. So this is going to factor as x minus 1 times x plus 1, and you're going to get x equal to 1. Sorry, that looks terrible. Ugh, terrible. Sorry, it looks awful. Ugh, and x equal to -1. And both of these vertical asymptotes have odd powers. So we know that we're going to get opposite behavior, meaning one side up, one side down. So I like to think of odd going with opposite. And then finally, the horizontal asymptote. Well, the degree on top is 2. The degree on the bottom is 2. So the degrees are equal. The horizontal asymptote is going to be y equal to, there's a 1 there and there's a 1 there. So again, I want to point out, you're not dividing the degrees. You're not saying it's 2 divided by 2. You're saying it's 1 divided by 1. It's the quotient of the leading coefficients. So your horizontal asymptote is y equal to 1. Your vertical asymptotes are x equal to 1 and x equal to -1. That's all there is to say about that. Sorry. No, I was going to say that we need to check whether the x-intercepts bounce or across. We're going to go through, but we don't have any x-intercepts, so nothing to check there. So that means this graph never touches the x-axis. Okay, that's fine. So let's see. We've got a y-intercept of -4. We've got no x-intercepts. We've got vertical asymptotes at 1 and -1. I am kind of stretching out the x-axis compared to the y-axis. My scale doesn't have to be perfectly 1-to-1. So there's my x equal to 1. We do draw vertical asymptotes as dashed, I should say. We draw any asymptotes as dashed lines. And then we have a horizontal asymptote of y equal to 1. Okay, so let's see here. I know I can't cross the x-axis. So if I start right here at my y-intercept, which I usually do, I cannot go up, 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 because I can't cross the x-axis if I don't have an x-intercept. So the only choice is to go downward. And then since x equals 1 is an opposite behavior vertical asymptote, I know the other side has to be upwards like that. And then as I move to the right, I'm going to get closer and closer and closer to my horizontal asymptote. Similarly, if I move to the left from my y-intercept, I have to go downward this way because I can't cross the x-axis. And then this is also an opposite behavior vertical asymptote. So on the other side, we're up. And then as we move way to the left, we're getting closer and closer and closer to y equal to 1. Two things here. Thing one, later on, either in this video or if I decide to make a second video instead, we will see that this function is an even function. It has symmetry across the y-axis. If you were to flip this function across the y-axis, it would look exactly the same. The second thing I want to point out is just talking about a little bit about why we talk about having a horizontal asymptote. So what we're saying really here is that if x is really, 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 really big, or if x is really, really negatively big, the y value is going to be very close to 1. Let me give you an example for that. If x was equal to, say, 1,000, and our function is still x squared plus 4 over x squared minus 1, then f of 1,000 would be 1,000 squared plus 4 over 1,000 squared minus 1. 1,000 squared is 1,000,000, so that's going to be 1,000,004 divided by 1,000,000 minus 1, so 999,999. And if we pull out a calculator, why is my calculator not right here? Terrible. I guess I'll use my terrible phone calculator. So, sorry, 1 second. So if we pull out a calculator and do 1,004 divided by 999,999, look how close to 1 that is. So that's the whole point, is that as x gets really, really large or really, really negatively large, the y values get very, very close to the horizontal asymptote. That's the whole deal. Later on in calculus, when we start talking about limits, we'll say, oh, the limit as x goes to infinity of this function is 1, because the function's values get closer to 1 as the x values get infinitely large or negatively infinitely large. All right, let's look at the reciprocal function. Let's take that previous function and flip it over and see how that looks. So same steps. We're going to find the y-intercept as usual. We're going to set x equal to 0. We're going to get f of 0 equal to 0 minus 1 over 0 plus 4. I didn't write 0 squared because I know 0 squared is 0, which is going to be -1/4. Okay, x-intercepts. Set the numerator equal to 0. It's going to be x squared minus 1 equal to 0. We already know how this goes. It factors as x minus 1 times x plus 1. So we're going to get x equal to 1 and x equal to -1. And both of those are going to be x-intercepts where we go through the x-axis because they both come from factors with odd powers. This is going to be a through, this is going to be a through. Vertical asymptotes, well, we should already know that we aren't going to get any because in the previous problem, when we set x squared plus 4 equal to 0, we didn't get any x-intercepts, right? We set x squared plus 4 equal to 0, we got no solution, so no x-intercepts. I should even write that here, no x-intercepts. In this example, when we set x squared plus 4 equal to 0, again, no solutions, so that means no vertical asymptotes. Sometimes that happens. Sometimes your rational function, often your rational function, won't have a vertical asymptote. And then finally, horizontal asymptote is still going to be the same as it was before because the degree on top and the degree on the bottom still match. And y is going to equal the coefficient here, 1, divided by the coefficient here, 1, which is just y equal to 1. Let's graph that. Let's see, I've got a y-intercept of -1/4, so I'm going to put it like right there. Doesn't have to be perfect, just close. X-intercepts are +1 and -1. Again, I'm giving a little more space to the x things because that's just usually how it works. And then my vertical asymptote, I don't have any. My horizontal asymptote is 1. So here's y equals 1. And this function is kind of boring, right? You have these 3 points. We know that they're through. So I start here. I'm going to come up and hit that point there and then go through and then get closer and closer and closer to my horizontal asymptote. Same deal to the left. I'm going to hit that point. I'm going to go through and then get closer and closer and closer to my horizontal asymptote. That's kind of it. Again, you can make sign charts if you want to. I don't think you really need to make sign charts for these. Yeah. This next one might be an exception to that. Let's see. Yeah, this one is a little exceptional. That's fine. So we want to graph this function 3x squared plus 6x over x squared minus 4x plus 4. So we're going to do the usual thing. We're going to find the intercepts. So y-intercept. We're going to set x equal to 0, and we're going to get f of 0 is 0 plus 0 over 0 minus 0 plus 4, which is 0 divided by 4, which is 0. I'll point out, because I think it's worth pointing out, that it's usually easier to find the y things if the whole function is not factored, whereas it's usually easy to find the x things if we do factor the function as much as possible. So if you actually if you factor out the numerator, you can pull out a 3x, and you have the 3x times x plus 2, and in the denominator, x squared minus 4x plus 4 factors as x minus 2 times x minus 2, or x minus 2 squared. So factoring out the whole rational function makes it easier to figure out what your x-intercepts are, right? Because if we set the top equal to 0, it's much easier to set the factor form equal to 0 and solve. Doing that, we're going to get x equal to 0. We're going to get x equal to -2. And both of those are going to be intercepts that have through behavior because that's x to the first, that's x plus 2 to the first. Like, I'm wondering, did they have any intercepts that had bouncing behavior? I might have not had the bouncing behavior here. That's kind of disappointing, James. Yeah, I might have to make up another example where we have a bouncing one. We'll see. So let's find the vertical asymptotes. We're going to set x minus 2 squared equal to 0. We're going to get x equal to 2, and it's going to have same behavior because it's coming from a factor with an even power. And then we have horizontal asymptote. The degree on top is 2, the degree on the bottom is 2, so we're going to get y equal to 3 divided by 1, the coefficient of x squared divided by the coefficient of x squared, to get y equal to 3. Those are all the pieces of information. So I should move this. The paper behind is kind of seeping through. Sorry here. So let's graph it. All right there. So let's see. We have a y-intercept of 0. We have an x-intercept of 0, of course, and also -2. Right? If y equals 0 is an intercept, so is, or sorry, if the y-intercept is 0, then one of your x-intercepts will also have to be 0. We have vertical asymptote of +2. And then we have a horizontal asymptote of y equal to 3. So let's see here. So this is where I probably would make a sign chart, or at least test another point, because from here, I don't know if I'm going to go up, I'm going to go down. And you might be thinking to yourself, well, James, you can't cross the horizontal asymptote. And I would say, well, actually, that's not true. You totally can cross the horizontal asymptote. It's perfectly valid to do. We might not, but it certainly can happen. So let's see. So if I plug in like 1, and this is where I'm going to write my function again. So my function, and it's easier to look at the factored form, 3x times x plus 2 over x minus 2 squared. If I plug in 1, 3 times 1 is positive, 1 plus 2 is positive, and 1 minus 2 is negative, but the negative number squared is still positive. So it's positive, positive, positive. So the whole thing's positive. So if I plug in 1, it actually is positive. So the graph does go up this way. And then since my vertical asymptote has same behavior, and it's going to also be going down that way. And then to the left here, well, since my intercepts have through behavior, I'm going to go through and then get closer to my horizontal asymptote like that. So yes, it's totally possible to cross a horizontal asymptote. We could have also made the sign chart. So again, on the sign chart, the numbers you're going to include are any x-intercepts, so 0 and -2, and any vertical asymptotes, +2. I know I know that's open because it's undefined there. So then pick a number larger than 2, like 3. Positive, 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 the whole thing's positive. And then you can either pick a number between 0 and 2, like 1, or you can say, well, at 2, the 2 came from x minus 2 squared. Since it's raised to an even power, we know we have the same sign. The sign doesn't change. 0 came from 3x to the first, odd power, sign changes, where you have opposite behavior or going through behavior. And -2 came from x plus 2 to the first. So again, sign changes. You either have opposite behavior if it's an asymptote or going through behavior if it's an x-intercept. So yeah, positive, negative, positive, positive. Kind of cool. I do feel like I should give one more graphing example so we have at least one x-intercept where we bounce. So let me just come up with one more example here real quick. Sure. Let's look at something like f of x equal to, let's make it interesting, James. Let's say we have x minus 3 squared over x squared. Sorry, I'm trying to think of something on the fly here. X squared plus 4x plus 3. Yeah, that'll be good. So let's find the usual things. Y-intercept, plugging in 0 for x, we're going to get f of 0 equal to 0 minus 3 squared over 0 plus 0 plus 3. That's 9 over 3, which is 3. Okay. X-intercept, just set the numerator equal to 0. You're going to get x equal to positive 3. And it is going to be a bounce because that 3 came from a factor that has an even power. Vertical asymptotes, we're setting the denominator equal to 0. We should definitely factor it. It factors as x plus 3 times x plus 1. So we're going to get x equal to -3 and x equal to -1. Both of these are going to be opposite behavior vertical asymptotes because they came from factors with odd powers. And finally, the horizontal asymptote, if you multiply out the top, the degree is 2, right? If we multiply this out, it's x squared minus 6x plus 9 over x squared plus 4x plus 3. Since the degrees are the same, the horizontal asymptote is not 1 always. It's 1 because it's the quotient or fraction of the leading coefficients, which are 1 over 1. Okay, let's go ahead and make the sign chart just so you can see what's going to happen here. I want to point out that whenever you bounce, you stay the same, or whenever you go through, you change signs. Whenever you have the same vertical asymptote behavior, you stay the same sign. Whenever you have the opposite vertical asymptote behavior, you change signs. So we have -1. That's a -3, although it looks heinous. Sorry, that's a -3. No, it's terrible, kind of. So -1, -3, and +3. So we have 3, -1, -3. We know when we plug in 0, the whole thing's positive. So it's positive between -1 and 3. We know if we plug in something like bigger than 3, in fact, I should make my life easier. I should write this as x minus 3 squared over x plus 3 times x plus 1. So I plugged in 5, positive, 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 the whole thing's positive. And then at 3, since it came from this factor with an even power, the sign should stay the same. At -1, since it has an odd power, the sign should change. At -3, since the factor came from a factor with an odd power, the sign should change. So it should be above, below, above, above. And we know that at at these places we have the vertical asymptotes. So you can kind of even see what's going to happen, right? It's going to be above, so it's going to have the vertical asymptote up like that. Then it's going to be below, so vertical asymptote like that. Still below, so going down like that, and then above, and then it's going to bounce off and be above. So it's kind of, again, not, oops, stop, my video, you're killing me, video. So as I was saying, you can make a little sign chart where you have your x-intercept and your vertical asymptotes on there. And then you can even kind of draw a little picture. So we know like we have a vertical asymptote of -3, a vertical asymptote of -1, and an intercept of 3. And then we know it's positive, so it's above, negative, so it's below. So we have that opposite behavior, still below. And then at -1, we have the opposite behavior again. So then above, and then at 3, we bounce off. So it kind of goes up like that. Now, I know it's not a great picture. Also, it doesn't really go up like that because I forgot about my horizontal asymptote. So it should just like kind of leveled off there. But I'm just kind of looking at that to help me draw the picture. So now, if we actually graph it, we have our y-intercept of +3, our x-intercept of also +3, vertical asymptotes of -1 and -3. But as I was saying, we have our y-intercept at 3, our x-intercept at 3, our vertical asymptotes at -1 and -3, and our horizontal asymptote at y equal to 1. And then we can so I wouldn't actually use the sign chart to graph it, or at least I would say I wouldn't use a sign chart in general. I would just say I start here, and I have to go from here to there and bounce off. I'm gonna go like this. And then I don't have any reason to cross over the horizontal asymptote again, but I definitely did cross it somewhere here. Then here I'm gonna have to go upwards. So the vertical asymptote, you either have to go up, 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 or down, down, down. And on the other side, since x equals -1 is an opposite behavior vertical asymptote, we know we have to be going down like this. This is kind of the funky part here because you're going down and then you kind of have to just like change directions and go down again because there isn't an x-intercept to cross through. And then finally on the other side of this vertical asymptote, we have to be going up and then like that. Notice how it does look a lot like my sign chart. Okay, so that is graphing rational functions. I'll make another little video to talk about how even and odd functions work, but they're pretty straightforward once you know how to do it.